Check. Okay. Now. All right. Good. Yes. Welcome, everybody, to the second lecture of the course. So, just to recap, yesterday I sort of gave you I tried to give you a glimpse into what thermodynamics is about, what are the sort of questions we would then ask in quantum thermodynamics, and following that, I talked about the first technical concept that we had in the course, which is the concept of a thermal state. So I want to both repeat a bit that and expound on it to make some of the concepts clearer, and then continue in detail. So the concept of a thermal state . And yesterday, what I just stated the definition of the Gibbs state. So this is what one usually takes for microscopic thermodynamics as a thermal state. I said that if you have a density matrix rho and it's supposed to be thermal, so in fact we call it tau, then it is proportional to the exponent of the Hamiltonian of the system divided by, well, the partition function, which is just to say that it is a normalized state. Okay. Now, as the course goes on, we will actually justify this state and why this should be the thermal state. But I can sort of give you two reasons, which we will do in detail in the course. And the first is equilibration. And loosely speaking, this is the fact that if we have a very large, let's say, a very large quantum system, and I split it into sort of a little system that I want to study that I actually label S, and then the rest I call it an environment. And if I just pick this at random, so I say this room is my very large system, and I pick a single, let's say I had a cup of coffee here in front of me, I pick that to be S, and then the rest of the room is the environment. If you were to describe the Hamiltonian of such a system, what it would generally look like is that the Hamiltonian H would be something of the system, something of the environment, sorry, and some interaction term that we call HSE. Now, in fact, when I write HS, what I mean is HS tensor identity on the environment. And when I write HE, I mean identity on the environment tensor HS. I don't need to do this for HSE because I am actually assuming that it is an operator on both the spaces. Now, when we have such a split, and very important, we have an interaction term, because if I have a cup of coffee here, it's not isolated from the environment. It can exchange heat. It can also exchange particles, which maybe goes beyond this, but at the very least, it is interacting with its environment. And if I do this and I say, well, if I look at the state of this system, what can I expect it to be? And even if I start with the whole system and environment in a very pure quantum state, but now I just look at just the state of the system and ask what it's going to be, then what it turns out is that for most times, and when I say most, I mean, as the relationship between S and E becomes more symmetrical, it becomes very strong. So the smaller the system with respect to the environment, the statement that I'm making gets stronger and stronger. So for essentially ds much less than dE, rho s, which is the state of the system, let me write this on the next part. So ds much smaller than dE, rho s becomes very close. So for most times, let's say, times becomes tau s. Now, this is at the moment I'm making it a loose statement because when we speak about equilibration, all of these will become clear. So what exactly is in this inequality, what dimensions we compare, what does for most times mean technically, because we have time average states, and close to tau s, what do we mean, like how close within trace distance and stuff. But the physical content of that is to say that whenever I have a little system weakly interacting with a very large environment, it equilibrates in such a way that when I look only at the system, it looks like it's a thermal state. In particular, it looks like it's a Gibbs state. The fact that it looks like a Gibbs state and not something else comes from the fact that the usual thing that is conserved on the system and environment together is energy. And so that sort of singles out the Hamiltonian as being the most important. Yeah, but as I said, this statement will become clearer. The other way of looking at the thermal state, which is something we will do actually before equilibration, is as a free state. And there are many ways to see this as a free state. In particular, the notion of passivity, or actually I would say complete passivity. And on the thermal state, what complete passivity is the following statement. If I take as many copies of the thermal state as I like, so I have tau tensor n, so I have n copies of the thermal state. I do any unitary on this, and this is a joint unitary on all of them, any unitary operation, and I find out what the average energy is at the end. So H at the end of this. Now, H, remember, here is the sum of each individual Hamiltonian tensor identity on the rest. So this is the sum Hamiltonian. Then this is always going to be greater or equal to the average energy of the initial state. And what this is to say is, as many thermal states as I like, I can take together. I can make a unitary operation in it. I will never be able to extract energy. I can only put energy into a thermal state. I cannot extract energy out of it. So this, in some senses, in the course, it will be the first example of sort of a second law, because that one of the statements of the second law is one cannot take heat and convert it into work, which is why the energy that is stored in a thermal state is really the purest form of heat, because you can never use it to generate work. Okay, so this is a glimpse into why the thermal state is of this form and how we will justify it later. All right. So then a few properties of this. Now, if I have tau is equal to e to the minus beta hs upon the trace of the same. So this is diagonal in HS, but I would also add fully diagonal, and I'll explain what this is now. So in general, my Hamiltonian is going to be some, in the energy eigenbasis, when I write it, is some diagonal matrix. So imagine I take the example that I was using the other day. I have three states. The first state is there's a ground state, so it has zero energy. And the two states after have the same energy. So this is the energy level diagram, one ground state, two degenerate excited states. Right? So when I do this, the point is that if I take tau now in this basis, it's going to be 1 upon the partition function, 1 e to the minus beta e, e to the minus beta e. Okay. Now here's a very important fact. For every energy that is the same, the thermal state has the same population because it's exponent of beta e. And what this means is that we know from linear algebra that if we have a degeneracy in states, we are free to choose a basis. So I need not pick my basis to be, so if I call these states 0, 1, and 2, off the board, 2. I could, for the Hamiltonian, equally pick the bases 0, 1 plus 2 upon root 2, and 1 minus 2 upon root 2. This is also a valid base for the Hamiltonian. The Hamiltonian would look exactly the same because the eigenvalues are degenerate. So from linear algebra, we know that we can construct other states of the same eigenvalue by taking superpositions. And now I could say, well, tau looks diagonal in this basis, in the 0, 1, 2 basis, but what happens if I change it to the other basis? And the answer is it does not change. It looks exactly the same. And the reason for this, if you look at it on a mathematical level, is that within the subspace that is degenerate, all the populations are the same. So it's e to the minus beta e, e to the minus beta e. So within that subspace, really what it looks like is proportional to the identity matrix. So you can just take the population times the identity matrix within that whole subspace. And when you change a basis and you do a unitary matrix, nothing is going to happen because the identity matrix looks the same in all bases. So within a degenerate subspace, tau is diagonal regardless of the basis you choose for the Hamiltonian. This is not true for any other general state. So for instance, I could have another general state where I put different populations in the second and third state. It would look diagonal in the 0, 1, 2 basis, but then if I change to the 0 and these superpositions of 1 and 2, it would then no longer look diagonal. So this is an important distinction. Any questions? So I'm going to keep that there as a reminder. Okay, so right. So the next thing we talked about is a virtual qubit. Oh, actually, let's talk about the real qubit first. So a thermal qubit. And that was, so we have a Hamiltonian, which is just E1, 1. So it's the same as saying you have 0, 1. And the energy gap is E. And for a thermal qubit, we wrote the state tau is simply 1, well, let's say 0, 0 plus e to the minus beta e 1, 1 divided by 1 plus e to the minus beta e. Okay, yeah, very important. This is a diagonal matrix. So this is 1 upon, let's say, okay, 1 upon z. So then that's 1 e to the minus beta e, 0 and 0. Okay. And of course, so the only degree of freedom, once you put these two, the off diagonal terms to 0, is of course just the temperature that determines. Hello, this board does not like to stay down, right? Yeah, so it's the only degree of freedom is the temperature that determines the ratio between these levels, which also meant, and this was the thing that I said, that any diagonal density matrix rho for a qubit is thermal. Now, I just want to remind everyone that I'm working really exclusively in the energy basis. So when I say diagonal, it means at the energy basis. And in fact, it has to, because if I said diagonal in general, that doesn't have any meaning because you can always change basis and make it off diagonal. So if I say it without specifying further, it is in the energy basis. Right, so every diagonal density matrix of a qubit is thermal. And I think you did a problem yesterday that sort of shed light a little bit on beta, but I'm going to draw the scale as well now. So now I can just consider some limits. Imagine that imagine that I want to find out what beta is for the ground state of the system. So if tau is a state that is entirely in 0, so there's no population in 1 and all of the state is really a pure state of 0, what will beta look like? Well, that means that the amplitude of the 1 state must go to 0, or the population in the 1 state must go to 0. This value must go to 0. So beta must go to plus infinity. So if this is the scale for beta, and this is plus infinity, this is the ground state. Now, as I decrease beta from positive infinity, the value of the amplitude in 1 begins to increase gradually. If I wanted the amplitude of it being in 0 and 1 to be the same, so for example, the same property of being in either the ground or the excited state, then I would have to make, well, since the amplitude here, at least in the numerator, is 1, this has to also be 1, and therefore beta must be 0. So 0 is the maximally mixed state. And now comes something that actually does not happen usually for classical thermodynamics. It cannot happen for particles of a gas. I can now make beta, I can take beta beyond 0, and I can make beta negative, in which case the amplitude of being in 1 is now greater than that of 0. And as I do this, there's going to be more population in the higher state. So this is what you call an inverted state. So this region here, you can refer to as inversion. And all the way at minus infinity, I have the excited state. Now, one could imagine, well, why doesn't this happen for systems that we treat in normal life? And the reason is very simple. It's because the Hamiltonians we're used to are unbounded. And when the Hamiltonian is unbounded, you can never go to negative temperature. And the reason is the following. So imagine that I took the harmonic oscillator Hamiltonian, so this is simply sum from n0 to infinity. So this is the harmonic oscillator of n omega nn. Now the problem is, if I take the state, the thermal state, which I construct here, so it's proportional to, it's going to look at sum of n e to the minus beta n omega n n. And this is all the way from n is equal to 0 to infinity. There's a proportionality outside. And now I consider what happens if I take beta towards 0, which is the point where if I want to go to negative temperature. And the problem is, if I take beta towards 0, this would take all of the factors here to the same number. This would take all of the factors to 1, regardless of what n and omega is. But that would mean that every level was populated equally, which can never happen because I would need infinite energy. There's no bound to the highest energy level. So as beta tends to infinity, sorry, not to infinity, to 0, the average energy E goes to infinity in this case. So for anything with an unbounded Hamiltonian, you only have positive temperatures, which is why most of classical thermodynamics only deals with positive temperatures. Which is also why in classical thermodynamics you can talk about it as T as the temperature rather than beta, because you only are dealing with 0 to infinity. When you deal with quantum thermodynamics and negative temperatures, it becomes clear that beta is slightly more preferable, and the reason is the following. Beta just above 0 and beta just below 0 are states that are very close to each other. They are states that are just slightly biased towards the ground or slightly biased towards excited, which means effectively that if you were dealing with T instead of beta, you would go, well, you go to plus infinity, and then the next thing is negative infinity. So the temperature scale is clearly discontinuous somehow, whereas beta is continuous. All right. Any questions? All right. So that was the real qubit. And now let me talk about a virtual qubit. So let me stay with yellow. Now, thermal states are very useful, but the problem is that most states are not thermal. And in particular, when we construct thermal machines, the inner workings of the machine cannot be a thermal state, because a machine is usually connected to multiple thermal environments at the same time. So the global state of the machine is going to be something very complicated. And the reason why looking at subspaces within the machine and understanding them as thermal is important is because you can actually see that subspaces in the machine are acting to sort of create temperatures that are useful for you. And so this is why we define the notion of a virtual qubit. So what I need in order to define a virtual qubit is I need, let's take rho of a system. So now my system is can have a Hamiltonian of many energy levels. So in general, so this is some Hamiltonian HS. And I pick from HS, I pick two levels. And I'm going to call them, let's say, M and N. So this is the levels corresponding to EM. This is corresponding to EM. So I've just picked two energy levels, EM and EM. And now I'm going to say, well, I'm going to take that rho of the system. So my density matrix of the system is block diagonal with respect to M and N. Now, mathematically, what this means is that all of the density matrices rho, all of the density matrix elements rho Mi is equal to 0, as well as rho Im, as well as rho rho Ni and rho In for I not equal to M or N, and also rho Mn is equal to rho Nm is equal to 0. So what I've done essentially is I've said the coherence, so the off-diagonal elements involving the energy levels M and N are all 0. So within that subspace, they are the state is completely diagonal. It can be something very complicated otherwise, but within that subspace, it's completely diagonal. So one such example. Oops. All right. Guess I have to go the whole board. So let me give you a simple example. Let's say rho S is a 4-level system, and this is, let's say, 1/2, 1/8, 3/8, sorry, that's 1/4, 1/4, and then I have 1/8 I and minus I/8. Okay, and the rest are all 0. Yes, it's a valid density matrix. Right, so in this case, 2, so rho S is block diagonal with respect to 2 and 4. You see it? Because the second column, everything is 0 except for the diagonal element. The fourth column and the fourth row, everything is 0 except for the diagonal element. Now, the thing about block diagonal is the reason that the phrase is block diagonal is because when those two elements are together in the density matrix, they're adjacent, you can really draw a block around them, and you see that it's sort of 0 everywhere else emanating from the block. But the point is, you do not need them to be next to each other. They can be sort of further apart on it, and it still works. The definition is still the same. Okay. Now, the reason this is good is because then when you look at these two energy levels, it really looks like the diagonal state of a qubit. So now if I look at that just for 2 and 4, what I have is sort of an effective density matrix of 1/8, 3/8, 0, and 0. And so now what I say is, well, let me try and understand this as a thermal system. And so I say, well, there is a delta E, the energy difference, which is E. So, okay, continuing with our language, I'm going to call this 0, 1, 2, and 3. Or, okay, since I started with 2 and 4, I'll call it 2 and 4 this time, but I should have labeled the ground state 0. Doesn't matter so much. So let's say E4 minus E2. And so I can define now a virtual temperature, beta 24, which is defined from the usual Gibbs ratio, P4 upon P4 upon P2 is equal to e to the minus beta 24 P4 minus E2. Now, it's very important. So the one thing that's very easy to see is that the definition of the virtual temperature does not depend on whether I write 2 or 4 first. Because if I flip the indices 2 and 4, in the left-hand side, I will get the inverse of the Gibbs ratio. But on the right-hand side, I will get the negative of the energy. So the equation will still be the same. And so beta will not change. It will not flip sign. So this is very important. You do not need to know whether E4 is larger than E2 when you write this equation or not. You will still get the correct virtual temperature either way. Because if it is smaller, then this will be a negative number, and this will be the inverse of the ratio, and therefore beta will remain the same. So in other words, this is to say beta 24 is the same as beta 42, and therefore there's no ambiguity in there, right? Another way of saying this is that the virtual temperature cares about the ratio of populations compared to the difference in energy. So it's asked the question, does the higher energy level have the smaller population or the larger population? That's all it cares about. And then it does not matter whether you knew in the beginning which one was larger. All right. 12. So to end with, let's have an interesting example now of a 3-level system. So, let's say a qubit. I'm going to take a qubit, virtual temperatures, but actually yes. All right. So now I'm going to take my Hamiltonian of my system to be a 3-level system. So it is going to be 0, 1, and 2. So 0, 1, 2. It's 0, E1, and E2 being the energies. Okay. And now I'm going to look at, so I can define now my 3 virtual temperatures. I say P1 upon P0 gives me e to the minus beta 0, 1, E1. So it's E1 minus E0, but E0 is taken to be 0, so it's fine. And P2 upon P1 is equal to e to the minus beta 1, 2, E2 minus E1. Okay, now I can do the same and say P2 upon P0 is equal to e to the minus beta 0, 2, E2. But also, I can also calculate P2 upon P0 from these 2 equations. Because if I have the ratio P1 upon P0 and P2 upon P1, I can multiply them to get P2 upon P0. So clearly what we see now is that these 3 values are not actually completely independent. The third one is given by some sort of function of these 2. I'm going to check this now. I'm going to multiply the 2 equations together to get P2 upon P0. And the third one is already P2 upon P0. And so what I get is that P2 upon P0 is both equal to the product of these. So e to the minus beta 0, 1, E1 minus beta 1, 2, E2 minus E1, and this is also equal to the third one. So e to the minus beta 02 E2. So since these two things are equal, I can now simplify it. All right, I'm going to take this out because I just wrote it on the previous line. So these are both equal to each other. So of course, if the two exponents are the same, then what is in the exponent is also the same. So I get the following equation: beta 02 E2 is equal to beta 01 E1 plus beta 12 E2 minus E1. Okay, I've taken them out of the exponent. I've also flipped the negative signs on all of these. And so beta 02 is equal to beta 01 E1 by E2 plus beta 12. And I'm going to write this as 1 minus E1 over E2. Okay, now, at the moment, it just looks like a function, but one very important thing to understand is that, so if I can also now write this as beta 01, let's call this Q, and then the other one would be beta 12, 1 minus Q, where 0 is less or equal to Q is less or equal to 1. Okay, so here by design, now I said the betas are, they don't depend on whether we knew the energy levels, but now I actually want to make a point as to when energy levels are the sum of each other, what happens. So here it is really the case that E1 is greater than 0, E2 is greater than E1. And so these numbers Q and 1 minus Q, they are both between 0 and 1. So what this is now is what we call a convex combination. So convex combination, for those who have not seen it, is a special type of a linear sum where all of the coefficients are between 0 and 1, and the sum of the coefficients add up to 1. So it's basically like taking a probabilistic mixture, because each of the coefficients you can understand as probabilities. And the important thing about convex combinations is that when you take a convex combination of a set of numbers, you get something that lies within the set, which means that beta 02 is within the range of beta 01 and beta 12. Now, that means there are two options. If beta 12 is the larger one, then it means that beta 01 is smaller than beta 02 is smaller than beta 12. But of course, it could be the opposite. This could be the smaller one, and then this one is greater. But whatever it is, it's in between. Okay. So now I do this with this one example, but you could imagine that I had a very, very big system, and I just picked two energy levels in such a way that they shared a common energy. Like here, I picked 0 and 1, and 1 and 2, so that 1 was common. And I would get exactly the same relationship. I could take the virtual temperature of one of the transitions, the virtual temperature of the other one, and the virtual temperature of the sum of the two transitions. And so I will always have this fact will always be true, that the virtual temperature of the sum of the transitions is in between the other two. Okay. Is there any question? But now the thing is, I can also invert this upon its head and say, imagine now I use two of them to solve for the third, but I could also do the opposite. I could use the second and the third to solve for the first. It's the same equation. I just choose which one I'm going to put on the left-hand side and leave on the other. The fact that beta 02 is within this range means that if I took beta 02 and any one of these, the third one would lie outside the range. So if beta 02 is within the range of that, then it means that other ones, stay with me. So in the same way, I can say that beta 01 is outside the range of beta 02 and beta 12. Yes. Okay, so in summary, if I have two transitions that sum up to a third, the virtual transition of the virtual qubit of the sum of the two is going to have a virtual temperature that's in between. But the virtual temperature of something that is the difference of two transitions is something that's outside. Now, this is very important because what it means is that at the moment I have only one system. But when I consider many systems together, which is something I will do in detail in the next lecture, what we're going to find is that by taking cleverly transitions from, let's say, a cold system and a hot system, I can generate virtual temperatures of two types. The not so interesting type is the one where I sum up the transitions from a cold and a hot path. And then what I get is something in between cold and hot. But if I take the difference between transitions of something from a cold and a hot system, wow, it really goes all the way back up. Okay. Then what I'm going to get is something that's outside of the range. And this is very important because we have the usual understanding that if I take a cold system and a hot system and I put them together, they're just going to exchange heat in such a way that they go to an intermediate temperature. But the reason that this happens is because this sort of interaction is usually not very well controlled. Like all of the energy levels just interact with all of the other ones. But if I'm able to take such two systems together and really control which transitions couple to which other ones, then what I will get in the joint system is something that can look very interesting. It looks like it's outside the range that I started with. And this is somehow the basis of all of the thermal machines. So to conclude the lecture, I'm just going to give you an example of what we could call a qubit. And this is really, I would say, historically, quantum information in quantum thermodynamics sort of grew in the last couple of decades. And yet there was this paper written about the qubit maser, which is from the 50s, that one could see as the first example of essentially somebody constructing a quantum thermal machine by using virtual qubits. And what they did is basically they took a Hamiltonian of a qubit, like I wrote. So I have energy level 2, energy level 0, energy level 1. And now they do a very clever thing. They say, they shine two sort of lasers at this or thermal environments. And the effect of that is to essentially thermalize subspace of their choice. So basically what I can do is I can shine a laser that interacts only with the energy transition 0 and 1. And by doing so, I'm going to influence 0 and 1 to have a Gibbs ratio that looks like it's at some temperature. And I'm going to call this beta C, because in fact they designed it to be a cold temperature. So this is in the next lecture, when we do qubit swaps, I will really give you the technical details of how you interact with the system to change its sort of populations in such a way that it looks like a certain temperature. But for now, imagine that I was able to influence this transition to have the temperature beta C. And the same way, I'm able to influence, so this is this transition here. And I'm also able to influence the full transition 0 to 2 to have a temperature of beta hot. So I hope this is visible. I wanted to use red because the association with hot temperatures. Right. And so now I ask, well, what is, and the interesting thing to us now is, what is the virtual transition of this one, the yellow one? So this is some beta, I'm going to call this beta V. And the question is, what is beta V? And I use exactly the equation I had there. What I'm going to get is that beta V is going to become, well, let's just write it. Beta hot times E02 minus beta cold E01 divided by, well, I'm going to say it's divided by the energy of this one, because what I have here is E12, but I can also write it as E02 minus E01. So this is another way of writing. So it's the same equation as there. I've just rearranged it. And now the point is that this is very controllable. In particular, what I can do now is imagine I take this to the limit. Yes? So E01 is E1. Yeah, sorry. Yeah, E01 is E1. So sorry. Right. I can write all of this as E2, E1, E2 minus E1. Thanks. Yes. Okay. So now imagine that the following. Imagine take beta C to be, so beta C is supposed to be the colder temperature. So remember on the beta scale, plus infinity, minus infinity, 0, this is cold. So this direction is cold and hot is in this direction. And we assume, given that we construct these machines using lasers and things that could actually be classical, that we cannot use negative temperatures directly. So whatever systems we have in the beginning are all with positive temperatures. So I take beta C to be some cold temperature. So it's very large. So I take it to be large and positive. And I take beta hot to be small. So something that's close to 0. So beta hot is quite small, beta cold is large. What is going to happen here? If beta cold is large, then this value is quite large. It multiplies E1. If beta hot is small, then this value is quite small. So this then tends to minus beta cold E1 upon E2 minus E1, which essentially can be a negative number. So the important thing is by taking beta hot hot enough and beta cold cold enough, I can make this virtual temperature negative. And this means that this transition is now more in its excited state than in its ground state. Now, when I say its ground state, I mean, when I look only at this transition, 1 is ground and 2 is excited. Meaning that if I couple this somewhere else, it looks like it has energy to give. So this is what I mean by quantum maser. You've essentially created a source of energy within the qubit by using positive temperatures themselves. And this is the whole purpose of virtual qubits. Once you understand how subspaces in large systems look like they're thermal, and you understand how to bring them together in ways which, well, essentially are just linear combinations, you see the whole purpose of this is to build transitions of any temperature you like. And so this was the first example, essentially historically, of a thermal machine. And I will conclude by saying, as a simple experiment, you can just take exactly this calculation, and I'll just invert beta cold and beta hot. Just say, imagine that I made the blue, the 0-1 transition hot, and the 1-2 transition cold. You would then see that you could turn this into a refrigerator. Essentially, you could make the transition 1-2 as cold as you like something that was almost entirely in the lower sort of state. And so, in summary, a thermal machine is constructed, a quantum thermal machine is constructed by taking temperatures that are within the range that you have accessible to you, and then connecting them in clever ways to get things that are outside the range, either much colder than the ones you started with or much hotter than the ones you started with. And if it's hot enough, it then becomes a negative temperature, which is an inversion. All right, so I will conclude there and ask you if you have any questions about this. Yes?
Well defined when we have this block diagonal form.
Yes, this is true. Yes.
But for that matrix, we have the left 1, 3. Are they also in this form, or you require that they're strictly only elements on the diagonal, or only in the block?
Yeah, they are not of this form. So you cannot really use it when it's not of this form, because the point is that the state itself is changing, and because of the coherences and stuff, any sort of unitary that you do is going to interfere with the off-diagonal elements. So in the next lecture, what I would be doing is the basic operation of taking 2 qubits and swapping the states of them, which is how you essentially make a thermal machine work. You have something you've constructed, and then you have something you want to act on. But this, of course, depends. It also involves the off-diagonal elements. When you have no off-diagonal elements, you know exactly what's going to happen. When you do have them, then things get more complicated. Yeah. So. Yes?
Currently, that always when you are working with qubits, like using virtual qubits, sometimes because your 2 steps.
Yes, Indeed, yeah. So in principle, yeah. If we could only work with real qubits, then that would be very limited. And yeah, the whole purpose of this is that now we can work with anything as long as we understand qubit subspaces. Yes, but yeah, in general, we're always working with larger ones. Well, so having said that, the simplest autonomous thermal machine, it just uses 3 qubits. But of course, the point is to say then that the joint system, in fact, is now an 8-level system because it's 2 to the power 3. And so indeed, we look then at the virtual qubits within this 8-level system. So yeah. Perfect. Actually, I haven't checked outside the door what the next lecture is because officially our office hours are 15 minutes from now, right? Because, okay, if there is no lecture outside the door, what I'm going to do is I would just wait here so that I would be online for the office hours. But if anybody wanted to ask questions also in person, that would also be all right with me. But of course, if there's something there, then I would run back to the office in order to be able to be on the screen for anybody who wants to join online. Yeah.
Yeah. One more thing. This is just my personal statement. It's not representing ETH or the other lecturers in any way. We woke up today to news of war in Europe to a scale that we have not seen in generations, and it's very frightening. Just to say, like, we don't, like, I don't know what power I have or how much I can help, but if anyone needs help related to this at any point, like, you can come over. I don't know, like, if you're Russian nationals and you're worried you'll be drafted, or if you need an invitation from ETH to get someone out of Ukraine or anything that can be done, like, yeah, we'll do what we can.
All right, thank you very much.